Okay, you're looking at the earthquake machine. I call it QuakeCaster. And this contains all the essential elements of an earthquake. And there are only 4 things here. And if you have all of those 4 things, you get earthquakes. If you're missing any one of them, you don't get earthquakes. So what are they? Well, first, there's a steady motion of the interior of the Earth's tectonic plates. They're moving millimeters per year every day. And that's represented by this casting reel that I'm slowly, steadily cranking. And that's attached to a non-stretch line. And then it's connected to a rubber band. That rubber band represents the rubberiness, the elasticity of the Earth's crust. Believe it or not, the crust is rubbery. It's just very stiff rubber. Okay, what else? Then we have these kitchen countertop samples. They're the mass that's going to be moved in an earthquake. I've sandblasted the bottom of them, so they're rough, and they're sitting on top of an industrial non-skid surface. So that's the friction on the fault. So that's our fault, if you like. So those are our elements. And now what I'm going to do is just crank steadily, and I want you to just watch what happens. Okay, so we cranked for several hundred years, and then we had an earthquake, and then we waited some more time, and we had another earthquake, right? Okay, so let me ask you a question. Were all the earthquakes the same size if we measure size by how much it slipped? No. Were all the earthquakes separated by the same amount of time? No. Well, this is very bad news. If I can't make regular repeating earthquakes here with Home Depot sandpaper, a rubber band, and kitchen countertop samples, we're never going to get it in the Earth. Because in the Earth, there's much more variability. The rubberiness comes from the rock materials. We have granite, basalt, sediments. They're different. The friction on the fault is very, very uniform to the feel of my hand here. But faults are grungy, and they have bends and breaks, and some are slippery and some are rough. So that's also going to be more variable. So that's an indication for why we can't predict earthquakes, why we can never talk about a fault being 9 months pregnant, let alone 10 months pregnant. They're not that regular, and there's too much variability in the system. Nevertheless, we can say certain things. For example, if instead of a 2-bricker, we have a 1-bricker here, I'm going to take one of the bricks off. Okay, now if I crank at the same speed, the same San Andreas speed of 1 inch a year, am I going to get earthquakes that are more frequent or less? What do you think? Are they going to be larger or smaller? Okay, so now let's watch. So they're much more frequent and they're much smaller. And that makes sense because this is a force balance. It takes less tension on the rubber band to get this guy to go, but since we haven't stretched the rubber band as much, it doesn't go as far. So same fault, same friction, same elasticity, but I can get, let's say, magnitude 6s rather than magnitude 8s. And this is exactly what we see on the San Andreas. We have that place on the San Andreas. It's called Parkfield in the center of the fault. It produces 6s every 20 to 40 years rather than going all the way up to 8s that occur every, let's say, 200 to 400 years. Okay, well, what about this? What if I actually, you can see that I've sandblasted the bottom of this, but the top surface is shiny and smooth, as one would expect for a kitchen countertop. So what if I turn this guy upside down? Now, one side of the fault has almost 0 friction, and the other side is unchanged. Now what am I going to get if I again crank at the same San Andreas rate? Are they going to be still smaller, or am I not going to get earthquakes at all and it'll just creep along? Let's take a look. So it's almost now perfectly creeping, although there is a little kind of staccato chatter of it. And we have such a section on the San Andreas. It's called the creeping section. Again, same fault speed, same elasticity, but one side of the fault only has very low friction, has clay minerals in it. So we get this enormous diversity of behavior from the same conditions. Well, faults aren't necessarily in isolation. So what if I connect up to make a series? So now we have the San Andreas is 1,000 kilometers long, but we have earthquakes that are considerably smaller than that total size. So now what am I going to get as I start to crank this? Who goes first? Who goes second? Who goes third? All right, so think about that, and here we go. So that's interesting, right? This guy went first, second, and third, and he finally loaded the second guy up enough to go, and when he went, in some cases, all three would go together. And this further complicates the problem of earthquake prediction because no little earthquake knows it's marked for future greatness. Once this loads this one, it may or may not bring its sisters along with it. So we are more typically going to get individual ruptures separated by a lot of time, but sometimes they can all go together, and this happens on the San Andreas and other faults as well too. Okay, but I've still simplified the world because I have one fault that can just rupture down the way. And a better description would be a fault is in some kind of network where all these little parts are interacting. So that's what I want to show you next, and it's called fishnet stocking stress.